Well, good evening. I'm Charles Schultz, and this is the Randomizer for the 28th of April, 2022. And tonight we're going to discuss the term isomer. Now, isomer is an interesting term, and it's one that you generally will only find in biochemistry, although it's used in some other places as well. Its roots are in the Greek language, and it means isomer having the same share. Isos is a Greek word meaning same, and meros is a Greek word meaning share. So isomer means having the same share. And what this is, you often have chemical compounds that have the exact same chemical formula, but have a wildly different structural formula or a mildly different structural formula. So molecules that have the same chemical constituents, the same number of the same atoms, might be put together in many different ways, just like you can take a handful of Lego blocks and put them together in many different ways. So an isomer is a molecule that is one of those sharing the same chemical formula, not the structural formula. And we'll talk about that in just a moment. So come to schultzlaboratories.com or universesciencecenter.com. Explore our galleries, our 3D virtual environment for learning and for experimenting, and have some fun with it. Put on an Oculus if you have a 3D headset, wander around, have some fun, play with it, show it to your kids. Let them learn from it as well. We have subjects ranging from robotics to space to electronics to chemistry, and we're adding more galleries all the time with interactive exhibits. And if you are an educator and you wish to share some of the things that you learned in your life, we can set you up with a virtual gallery to display your works in a virtual classroom to share your teachings with others all over the world. We have our randomizer show weekdays at 6 p.m. Eastern Standard Time, where we pick a random technical term and talk about it and its applications. And also, we have our robotics lessons on at 9 p.m. on Mondays. Those are continuing. We're going to lesson 4 on our next class. Join us. It's a lot of fun. You'll learn a great deal of things that you'll really have fun with. It will enrich your life and it will help your understanding. Meanwhile, let's get back to the definition of isomer and what it's all about. If you look at molecules, and a lot of people don't necessarily know much about chemistry, but molecules sound like an interesting thing. If you look at a molecule, you'll find that it has a specific structure. It's assembled in a particular way. Now, for most minerals or inorganic materials, this isn't very important. But for organic chemicals, it is crucial. So in organic chemistry, we're looking at molecules based on the carbon atom. And the reason is carbon has 4 bonds available with any carbon atom, and those bonds can stick to almost anything. So you can make complicated molecules out of carbon very easily. Now, the 4 big atoms that we use, the 4 elements that are most pervasive in the structure of living material or organic molecules, are carbon, hydrogen, oxygen, and nitrogen. Now, of course, there are often other atoms required to make complicated molecules, but we're going to stick with the big 4 right now. So out of carbon, hydrogen, oxygen, and nitrogen, nearly every organic compound that you see consists almost entirely of those atoms, if not entirely of them. And one of the things that we've discovered is that many molecules can have the same atoms in their recipe, but moved around a little bit. So we're going to look at how this can work, and we're going to use alcohols as an example. Now, an alcohol is generally an organic compound that has 1 or more hydrogens and 1 or more carbons at its heart, some hydrogens stuck on it, and then an OH, a hydroxyl radical, stuck on there somewhere. So to put it to a little clearer explanation, methane, the simplest hydrocarbon, has a single carbon atom with its 4 bonds, and each of its 4 bonds has 1 hydrogen stuck on it. So a methane molecule has a carbon in the middle and 4 hydrogens. I could take one of those hydrogens off and put a hydroxyl, an OH, on there instead, and it will become methyl alcohol or wood alcohol. This is a toxic compound, but it's the simplest alcohol. What if I had 2 carbons and I did the same thing? Well, 6 hydrogens will fit around 2 carbons stuck together, and that is ethane. Methane, ethane, propane, butane. There's a family of more and more complex hydrocarbons saturated with hydrogen. So saturated hydrocarbons is where we're starting. Methane, you pull one hydrogen off, put a hydroxyl on, it becomes methyl alcohol. Ethane with two carbons, you pull a hydrogen off, put a hydroxyl on, it becomes ethanol, ethyl alcohol. Ethanol is grain alcohol, or the stuff you'll find in whiskey. So ethanol is a two-carbon alcohol, and it is a very simple alcohol, and it has one hydroxyl and five hydrogens around it. If we go up one more step and realize for methane or ethane, there's no way you can move it around and change it to make it a different compound. Methanol and ethanol are the same. No matter how you put it together, it's the same molecule, and it's structurally indistinguishable from any other. But when you get to propane, the three-carbon version, and you pull a hydrogen off and put a hydroxyl on, you get propanol. Now, propanol is the simplest three-carbon alcohol, but there's a trick. What if, instead of putting the hydroxyl on the end carbon, either end, it would give you the same molecule, but what if I put it in the middle carbon? Now we have isopropanol. Well, when you go to the drugstore and you buy rubbing alcohol, it's isopropyl alcohol, isopropanol. That is the simplest organic isomer that you can make. So isopropanol and propanol have exactly the same chemical formula, but one has the hydroxyl on the end, the other has it in the middle. So you can see how that can be different. Now, when you get to more complex organic molecules, some of them have a left-handed and a right-handed version. These are called chiral molecules because they can have a distinct side of a reflection of a mirror. One can be reflected in the mirror and look exactly like its counterpart. So left-handed and right-handed molecules are stereoisomers. They are isomers, but stereoisomers. So why is this important? Well, when we look at life on Earth, we know that everything on this planet, everything descended from the very first primordial cell, shares a biochemistry. And in that biochemistry, it is written by the structure of the molecules themselves that we are made of left-handed proteins, left-handed amino acids, and right-handed sugars. Now, how do we know which hand it is? I mean, it's a molecule, right? There's a very simple way of telling. Stereoisomers have an interesting property. Many of them polarize light, and the light can be polarized to the left or polarized to the right. The physicist, I should say the chemist, Louis Pasteur, who was the person who originated pasteurizing milk to make it safe to drink, Louis Pasteur studied stereoisomers. He studied molecules that showed a polarization of light. He found that if you were to take the compound tartaric acid and crystallize it, only the left-handed tartaric acid molecules would stick together in this crystal, and only the right-handed ones in this crystal. And you literally could sort the crystals out when the acid crystallized. You could pick it up with some tweezers, shine some light through it, and see which way it polarized the light. Now, this is an interesting thing. If you were to find a sample of organic matter and it was left-handed polarizing the light, then you would know that it came from actual living organisms or a deliberate process to sort the molecules. If you find a mixture that's made by random chemical processes from the raw atoms, the raw constituents, it will be a mix of left-handed and right-handed molecules called a racemic mixture. So a racemic mixture simply means it came from a chemistry process and not a biological process. And so we can distinguish a sample of organic molecules that came from random chemistry but happen to be organic molecules, or those produced by an intentional project, such as by the hand of man, or those produced by living organisms. This is very important. If we find a sample of organic matter from off the planet, let's say in a meteorite or a sample from another world, and the polarization was clear, that it was not a mix of right-handed and left-handed molecules, that we would know that was the product of biology. So that's one simple signature we can look for that will ensure us that what we're seeing is from life and not random chemistry. So isomers can have other similar structures, the same formula and different assemblage, but not be stereoisomers of something. And to make it clear, when we look at the sugar glucose, now glucose does have a left and a right-handed version, and when you hear the term dextrose, what they're talking about is the right-handed version of glucose. So glucose has 5 carbons in a ring and an oxygen making a hexagon. And somewhere there's going to be a hydroxyl or a few hydroxyls, and the rest are going to be hydrogens. Glucose has a specific set of hydroxyls in a certain arrangement with respect to that oxygen. But if you move it around a little bit, you can get other sugars that are perfectly acceptable, like galactose or mannose. These are all isomers of glucose. So glucose has 8 distinct isomers that are not glucose at all. They're similar, and they can function the same, and they are sugars, but they don't have exactly the same molecular properties. So when we look at glucose and its 7 other isomers, we also know that because of their complexity, they do have mirror images, stereoisomers. So when you take the molecule of glucose and you look at all its varieties and reflective varieties, you end up with 16 distinct isomers. 8 are stereo images or reflections of the other 8. So now, organic chemistry often has molecules of the same structure, but by moving the radical around and changing the structure a little bit, you will change such things as its melting point or solidifying point, its boiling point, its freezing point. Many properties will change, and sometimes it'll be just enough so that that isomer cannot participate in a chemical reaction the same way, or it may participate more aggressively or not at all. So it's strange to think that a very minor change in the structure of a molecule, which has exactly the same chemical formula as another one, will change whether or not it can even participate in a reaction. Biology depends on isomers, isomerism, and stereo molecules as well. And some of the products of our life are the discovery of the fact that some sugars can be mirror images and taste exactly the same. They can be sweet, but our bodies don't have the enzymes or ability to digest or use them. When the first search for life on Mars occurred, the doctor who came up with the process for locating that life and designed the machinery to do it was Dr. Gilbert Levin. And one of the experiments he wanted to carry out was to have a vial of left-handed sugars and a vial of right-handed sugars. So the experiment could be done twice, and if it reacted only in one of those circumstances, it would absolutely be proof that it was due to life and not chemistry in the soil. NASA rejected this proposal and went with only one type of food. So Dr. Levin was forced to make a racemic mixture, a mixture of left and right-handed sugar molecules to ensure that if the experiment were done and life were present, it would at least have something to eat and the signatures of its biology would at least be that clear. And this experiment was carried out in 1976 on Viking 1 and Viking 2, and in both cases, it succeeded. They took a sample of the soil, dropped it into the container with the sugars, which were tagged with radioisotope of carbon-14. When the gas was emitted through metabolism, the radiation counts went up just as predicted. They could tell that something appeared to be consuming it. They later dumped the system, started with another fresh sample of soil, which was baked at over 160 degrees centigrade for 3 hours to sterilize it if there were living organisms in it. When the experiment was repeated with the sterilized soil, no reaction occurred. That's a pretty firm indicator that they actually had life, all identified through the use of isomers, in this case, stereoisomers. So isomers are molecules with the same chemical formula, but a different structural assembly or order of assembly. And stereoisomers are the same thing, only there's a left-handed or right-handed mirror image molecule involved. So I hope that you've learned something about isomers and stereoisomers and the etymology of the word. And if you have any questions about isomers, the floor is open. So please proceed if anybody has any questions. Meanwhile, I'm going to encourage you to go to universeciencecenter.com or schultzlaboratories.com, sign up for our classes, sign up as a student member, support our growth. Help us become a larger and more effective facility for teaching people all over the world in a virtual environment that many children and young people find as engaging as a game. And think about it. The more time they'll spend in a learning environment, the more they're going to learn. I mean, it's a win situation all around. So, I don't see any questions or comments on the floor. I'm going to go to my, wait a minute, here we go. From Jim Diaz. Why did NASA disqualify the sample? Well, there were numerous instruments on the Viking landers capable of detecting organic life or organic molecules. They had a device called the GCMS, the Gas Chromatograph Mass Spectrometer, and it was supposed to be able to take a sample of organic material and identify it. It showed no result. In other words, no organic material in the sample of Mars when the GCMS was run. But there's a problem. Organic matter falls from space all the time. It's created in space in the form of a set of molecules called tholin. So the raw volatile molecules exist in space, and the action of high temperatures such as 1100 C or static electric discharge or lightning, or ultraviolet light from the sun or from stars are all capable of forming organic matter from these molecules that exist naturally. This matter rains down on the Earth all the time. It rains down on all the planets. So the theory is it should be on the surface of Mars. When their instrumentation did not find organic matter, they said that what happened in the experiment, Dr. Levin's life detection experiment, must be wrong. It must be some aggressive chemical in the soil oxidizing the sugars. Now here's the problem with that. They felt that hydrogen peroxide in the soil, created by the use of ultraviolet and water molecules, was destroying the organic matter, or even perchlorate molecules would be doing it. The problem is there are molecules in the soil such as iron sulfate salt, ferrous sulfate or melantorite, the mineral, that actually destroys peroxide on contact. So hydrogen peroxide can't exist in the soil samples that they were looking at. But here's the other answer. When they were testing the GCMS with samples of organic material, they found that their material had plenty of organics in it, but the GCMS was blind to it. It would take over 10 million cells in the sample, 10 million microbes in the sample, in order for the GCMS to detect them. In other words, the instrument was a bum instrument. It was blind unless you had an incredibly high count of organic material or organisms in the soil. So the GCMS was blind, but NASA refused to consider that a disqualifying factor. Instead, they claimed that the instruments that Gil Levin designed had a false positive. Now, the interesting thing is, in tests on Earth, it was proven that Gil Levin's instrument always detected organic activity and never had a false positive. And it always failed to detect it and never had a false negative. So it is to date the single most effective means of detecting microbe activity. And later tests showed that it worked in places such as the Atacama Desert on Earth, and there were other circumstances as well. In my opinion, he actually did find bacterial life, and NASA has never yet, in the 46 years following, never yet sent another life detecting package to Mars, which really makes you wonder why. If we really wanted the answer, we could have it today. So I hope that answers your question. Now, since there are no more questions or statements on the floor, I'm going to read my quote for the day. And this is a very good one. All Scripture is given by inspiration of God and is profitable for doctrine, for reproof, for correction, for instruction in righteousness, that the man of God may be complete, thoroughly equipped for every good work. And that is 2 Timothy 3:16 and 17. Well, I imagine that puts a cap on it. And I would say that this has been a successful lesson, and I hope you learned something about isomers as well as the detection of life. And I'm going to call this a wrap. I want everybody to have a wonderful evening. I'm Charles Schultz with the Randomizer, and make the world a better place. Thank you.